Here I have an example of coupled rotational motion and what that might look like. So this is a really common system that you might see in your car or on a lot of machinery. It was really common in old manufacturing types of situations where we have some motor that's driving this pulley A, and that's connected by a big belt to pulley B that might be running your actual machinery or something. So your motor A, and then we can use this to scale up that motion to drive some bigger items. So we have a small pulley with a radius of 0.15 meters, and it's being driven by a motor such that it has a constant angular acceleration of 2 radians per second squared. And this problem asks, what is the velocity and acceleration of the belt? So any point kind of along this outside is where the belt is. What is the velocity and acceleration of this after the bigger pulley B has made one full revolution? This is a great problem on YouTube, especially. You can pause it at any time and see how far you can get in the solution. And I would encourage you to do that as we work through problems that are posted online. So take a moment to think about this, pause the video, and when you're ready, let's come back and talk about it. So the first thing we need to realize here is that these are coupled together, which means that how A moves is going to influence how B moves, kind of like it did in old pulley systems, the real pulley systems. And the way that it's coupled together is we can see that the tangential motion on A has to be the same as the tangential motion on B. So however this pulley is moving here, it also has to be moving down here. And so for acceleration, for example, we can say the tangential acceleration, I'll call it AT of A, has to equal the tangential acceleration of B. And if we remember our equations for tangential acceleration, it is just alpha r. So the angular acceleration alpha of A times the radius of A has to equal the angular acceleration alpha of B times the radius of B. So this is a great example of coupled motion. And in this case, we know the angular acceleration of A, we know the radius of A, and we know the radius of B, so we can calculate the angular acceleration of B. So we have 2 radians per second squared times 0.15 meters will equal angular acceleration of B times 0.4 meters. And this gives us an angular acceleration of B somewhere on the sheet of 0.75 radians per second squared. So this is one part of how A and B are related. And this is really helpful because now we know actually how far B went. We didn't know how far A went, but we do know how far B goes. So we can figure out what the motion is going to look like after B has made one full revolution. And the way I'm going to do this is I am going to use my omega squared is equal to omega naught squared plus 2 alpha theta minus theta naught. And I'm going to do this for gear B. And the reason I'm going to do it for B is because I know B goes one full revolution, and I now know the angular acceleration of B. So I'm going to put B's here. So my omega of B squared at the end of this motion will equal the initial omega B, and I think we need to assume it starts from rest. So let's go ahead and do that. Assume starts from rest. So that'll be 0 plus 2 times 0.75 radians per second squared times my distance here. One full revolution is 2 pi radians minus 0 radians. And so this will give me that my final angular velocity of B is 3.07 radians per most of the way there. I just need to figure out how these relate to the actual motion of the pulley. And again, as we said earlier, that motion of the pulley all around the edge of B and all around the edge of A is just that tangential motion. So for acceleration, the tangential acceleration is equal to alpha times r. So that acceleration will be our alpha b, 0.75 radians per second squared, times the radius, 0.4 meters. So that should give us an acceleration on the outside of 0.3 meters per second squared. And then for velocity, so this is the acceleration, we'll need to do the same sort of thing, and we can say that velocity is omega r in the same way. So now we know our omega is 3.07 radians per second, and our velocity, or our radius, 0.4 meters, and that'll give us a velocity of the belt around the outside of 1.23 meters per second. So good example of how we can couple things together. In this case, by having the outside have to have the same motion because it's coupled together by that belt. So knowing that whatever our motion at the tangential on gear A or pulley A has to be the same as the tangential motion at pulley B has to be the same as the motion of the belt all the way through.